Okay, let's start. So today I'm going to explain about our sixth project, right? It's actually seventh project. So let's think about the concept of length first. So length. So of course, length is an attribute you can compute for a curve. So in fact, we have to think about what is a curve. But let's think about the length first, and then, if we have time, think about the concept of curve. So the basic definition of curve is that it's an image of a continuous map from an interval, let's say A to B, to some n-dimensional space. So if it's two-dimensional space, then it's two-dimensional curve. And if it's three-dimensional space, then it's called three-dimensional curve. So when I say two-dimensional curve or three-dimensional curve, it doesn't mean that the curve itself is two-dimensional thing. We say that it's lying inside of two-dimensional plane. So how do we define a length given that such definition of curve? So one definition, but there are several definitions depending on your circumstance. Since we are defining our curve as an image of a continuous map, we can define in the following way. Let's say we subdivide our domain of map, which is interval from A to B, into n subintervals. So in order to split it into subintervals, you need n plus 1 numbers, and we say we took equidistant partition. So we take the subintervals to have the same length, and we define the length of a curve to be the limit of the sum of all line segments approximating the curve. So here's the picture. So if you have a curve from certain point to another certain point, let's say this is the starting point and this is the end point, then that is somehow parameterized by the interval. So here is interval from A to B. So the curve may have different speed at different point, but you can just split your interval, the domain interval, equidistance, and then it will split your curve. So I'm not saying your curve is split into equidistance, because the speed will be different. Speed at each point could be different. So you might have a slightly different length for each pieces of curve, but when you increase the number of subdivisions, then those lengths for lines or segment of curve will decrease. And when you take a zoomed in picture of each segment of your curve, it will approximately almost equal or almost equal as a line. So if you're taking this one piece and assuming that our number of subinterval is very large, then this is almost look like a line, although it's not going to be a perfect line unless the curve itself is a line, but we can approximate by the line segment joining CTI minus 1, CTI. So we can approximate the lengths joining these 2 points by the lengths joining these 2 points in line. So that's the line, the length of the line. Okay, so you know why we are taking the limit, because the line segment is not exactly the curve, but we can approximate by increasing the number of subdivisions. Okay, but that's when we have a curve merely given by a continuous map. But if we are given with the parametric curve, so in other words, the map that parameterize the curve is a function which is differentiable, then we can think about actual speed, actual instantaneous speed at each time t, right? So this is the displacement or position of your point on the curve over the time, or at the time t. But when you change the time, you change this position, displacement, or position of your point. And when you take the differential of that position, it's the velocity. Now, you don't want to integrate the velocity. Velocity is the vector. You only want the size of the vector, which is the speed. So when you integrate the speed, which means that you're just summing all the speed over the time, then you get the length. That the length that the point traveled from one point of the curve to another point of the same curve. So you're integrating the speed to get the length. So depending on what your situation is, you can either use this one or that one. But this one, the second definition, actually comes from the first definition, because when you look at this one, what is the meaning of the difference between the 2 points? So you're looking at the 2 points right here, and here you're actually looking at the vector, your vector, right? But this vector is approximated by some vector in between these 2 points. Let's say this is ti minus 1, this is cti. Now, you can use a theorem like mean value theorem, or you can also think about this as something like approximation. So I'm exaggerating here, but let's say I take a tangent line at the beginning, but although this tangent line is c prime ti minus 1, and that's different from the vector joining these 2 endpoints. But if you have a large number of subdivision, which makes the interval of subdivision to be tiny, then these 2 vectors are almost equal. So you can approximate this thing into c prime ti minus 1, or just ti, depending on which value you're taking. So if you're looking at this one, this is c prime ti, or if you're looking at the tangent vector at the beginning, it's c prime ti minus 1, but it doesn't matter because we're making this tiny segment even tinier. So anyway, so this whole thing is approximated by this one, or you can take any point in between ti minus 1, ti, so that it actually equals to this vector. So that's what comes inside here. So, and then look at all this limit and summation. It's the Riemann sum. So it's the Riemann sum. So you have to multiply with this one, the length of time, in order to approximate the actual distance. So anyway, the Riemann sum over the function c prime, the absolute value of the c prime value, the value of size of a vector, times the amount of time passed, is the integration of that function over the t. So they are the equal thing. Okay, so let's think about, let's go directly to our project issue. So our issue is to get the length of a curve, but in order to get the length of a curve in a different format, so besides taking this thing, we're going to approach in different direction. So we're going to use a line. We're going to use ideally all possible line on the plane. By the way, so what we are going to do in this project is to find the length of a line or curve lying inside a 2-dimensional plane, not 3-dimensional. Okay, so only the 2-dimensional. So we're going to use the line on the plane, and we need to parameterize. You need to identify the line. So the method of identifying a unique line is by taking the angle and the distance. So angle of a line is measured from x-axis, this x-axis, toward the positive direction, and the direction of a line. So here, I'm distinguish the direction of a line from its original direction to its opposite direction. So when you parameterize line, it doesn't matter whether you go to the forward direction or backward direction, but here we are taking a direction to be the forward direction of the line. So if you're taking the reverse direction, we are actually looking at different line. We'll see what it means. So anyway, let's say I take one vector, u, that is the forward direction of the line. Forward direction. And I'm taking the angle between these vector u and the E1 vector, positive direction of x-axis. That's our theta. So that's the theta parameter of a line, L. And that doesn't give you a unique line. We need the distance of the line from the origin. So it doesn't matter which point you choose, but I just take the origin as a standard point. And how do you measure it? It's the smallest distance, so it's the shortest distance from the origin to one of the point on the line. So it's going to be the length of a line segment passing through the line perpendicularly. So that's a rho. So theta rho gives you a unique choice of line. Why? So you can see that if I change the rho in this situation without changing theta, you can make your line move upward, right? Upward. So you can fill up all the lines with this specific angle above this line. But how about, what if you want to identify the line with the same slope, but in the below, lower than this line, the line that passes the origin. So then what you need is not taking the rho as a negative value. So rho is always taken as the positive value. What we are doing here is we're taking the theta to be added to the pi. So we are taking 180-degree flip of the line, of the angle, to get the another side of the line, right? So when I say this line, so angle is always measured from positive direction, which is positive direction of x, which is E1 direction, to the counterclockwise direction of the line. So when I have this line, so we have, this is my angle rho, and the angle is measured from here to here, because I'm taking this direction of line to be this. So this is my theta. So if you compare with the theta here and theta here, it's a theta plus pi. Okay? So I'm taking the rho from 0 to infinity. I don't have to specify infinity here. Then theta is from 0 to 2 pi. Of course, 0 and 2 pi are the same, but I will need to distinguish this one because it's only one point. It doesn't matter whether I integrate over with this theta rho domain. One point of overlapping, it doesn't matter. So taking just one positive rho and one value between 0 and 2 pi gives me a unique choice of line. So that's L. That's L. And given the curve C, I'm going to define an integer valued function, Ln, and this integer valued function is parameterized by theta and rho, which is the same parameter that parameterized the line, and it counts the number of intersection between the line L theta rho with the curve C. So I'll give you the example after this, but anyway, let's finish this statement. It's the Cocy-Crofton formula, or it's the theorem by Cocy-Crofton. It's a old theorem. Because you can Google how old is Cocy, mathematician Cocy. So, given that n, the function n, if we integrate that function over this domain, the domain for theta and rho, and actually it looks like it's an improper integral because we are taking the interval of rho from 0 to infinity. So whenever you see an infinity in the bound, then it means it's an improper integral, but it's really not an improper integral. We'll see shortly. But anyway, when we take the integral over entire domain of theta phi, and we take the half of that, it's the length of a curve. So it's quite a weird theorem. It's a weird theorem. But let's see how it works. So let's look at the simplest example. So I'm going to take a curve. It's as a line segment, a simple line segment. It's the line segment on the coordinate plane joining the minus L0 to 0, 0, and it has a length L. So of course we know the length, but we're going to use the Cocy-Crofton formula whether it gives the actual same length. So let's think about our function n. So here our function n, theta rho, is either 1 or 0, because as I said, it only counts the number of intersection with the curve C, so this is the curve C, with the line segment parameterized by theta rho. Because it's a line, so the curve is a line, any line intersecting the line cannot have more than one intersection, right? So always has a length value 1 or 0. So when does it have one intersection? So for example, let's say if I have a line segment with the angle theta like this one, then it can move up to this far, right? So if the distance is farther than this, then it doesn't have any intersection anymore. So how far it can move? So this is a theta, and the rho here is, so we know that this is L, so rho is L sine theta, right? So when I have a theta, so I'm assuming that this theta is, let's see, in between 0 and pi over 2, so theta can go up to 0 to L sine theta, right? So now let's think about when it's flipped, so 180 degrees. So we can take the theta to be 0 to 2 pi, but also we can take theta, the range of theta, to be minus pi to pi, the same thing. So when it happens, then let's see what happens. So if I have the line segment here, then I measure the distance from the origin to the line in this direction, that's my rho, and it can go as far as here, right? As far as here, and the maximum distance it can move is also, so since this is theta, also the sine, L sine theta, right? Because it's a theta and rho is an L sine theta. So I can move, I can only change my rho from 0 to L sine theta. Now let's think about how much can I rotate my angle in order to have at least one intersection. So if I have an angle in between minus pi over 2 to pi over 2, so it's something like this one, so it's somewhere in between here, so it always have some intersection. But what if I have the angle bigger than or less than pi over 2 or minus pi over 2? So let's see. So if I have angle bigger than pi over 2 but less than pi, so it's a little bit confusing if you're looking at this first time, but even if I confused also. So think about this carefully and then let me know if you have any question. So this is the direction where it's pointing to. So that's the angle, and angle is less than pi but bigger than pi over 2. And let's see. Sorry. So as I said, I always make mistakes here. So when you're looking at this picture, the measurement of rho, the distance rho, the line segment that has distance rho is always lies on the right side of the direction of your line. So when the line is moving this direction, the line segment that measures the distance from the origin to the line sits in the right side of the line. So when I make this picture, let me do it again. So when the theta is from between 0 to pi over 2, the rho can be 0 to L over theta, L times sine theta. That's right, because the line segment that measures the distance is on the right side of the line. Now, when I have the inverse direction, let's say I'm taking, flip side here, so I'm moving this way. So actually, this is not happening because when you are moving this direction, then you need to measure your distance from the line to the origin to the right side of your line. So this line is not actually the line segment that's pointing this direction, but it's actually pointing the upward direction here. So if you're moving on this direction, then now you can measure the line segment from the origin to the line here. So it's actually the line that has the angle between pi to pi over 2. So what happened to this kind of angle? Let's see. How about this one, for example? Well, that's below the x-axis here. So when you look at this line, this one, the red one, let me keep different color, then you are looking at the line whose distance from the origin to the line segment is here, and therefore the line was pointing this direction, so you actually have an angle of that line bigger than pi. So in that case, this kind of line, the red one, doesn't intersect the line segment that we are taking as C here at all, even if we increase the rho, because when you increase the rho, it gets farther and farther from the curve and never intersects the line segment here. Although when rho is 0, it intersects at the origin, but we're not taking care of that situation because that only occurs at one point, and the exception at one point doesn't affect the integral, so we're not taking care of that case. So anyway, so when does this one intersection happens? It happens when you have theta is between 0 to pi, and rho is between 0 to L sine theta, and except those cases, intersection never happens. Okay, so we have function n as this one. So we are integrating over entire domain of theta phi, but it's always 0 except these two cases. So it's actually same as integrating over this domain, so right here in domain D, the function 1, the constant function 1. So that's why when I say in the definition, in the formula, Cauchy-Crofton formula, even though the domain of integration looks like an improper integral because of the infinite symbol here, if you're taking a finite curve, at least your rho doesn't go to infinity, because if your curve sits inside of a big ball around the center origin, then outside of a ball, any line doesn't intersect the curve. So your rho doesn't go infinity to make a non-zero value of your function n. So you're actually taking a finite integral, the normal definite integral. So let's take the integration. So we have n equals to 1, it's constant 1, and let's take the iterated integral over this domain. So theta is from 0 to pi, and rho is from 0 to L sine theta. So just simple. So L times sine theta, when you integrate sine theta over 0 to pi, it's 2. So cancel out with 2, we get L. So it works. The Cauchy-Crofton formula works for simple line segment. Of course, we have to do something more. Let me take another example. So let's take a unit circle. So what's the boundary of the unit circle? It's 2 pi. The length of a boundary is 2 pi. So let's see if we get the 2 pi when we plug in our situation to the Cauchy-Crofton formula. So when you have a unit circle, the line intersect at most 2 points, and intersect only 1 point if it's tangent to one side. And let's see, when does it intersect? So here is a unit circle, and here's xy plane, and it actually intersects for every theta, right? So theta can be any direction, right? So if it's directing this direction, like with the positive forward direction this way, then it can move up to 1, right? So it can move its distance from the origin up to 1, and the distance is bigger than 1, it doesn't intersect anymore, right? So for any angle, you can move your line segment, distance of your line segment up to 1, so that you have an intersection. Okay? Now the problem is, if your rho, the distance is strictly less than 1, your number of intersection is 2. But when the rho is exactly 1, your number of intersection is 1. So you have 2 different values. So the problem is, should I distinguish the cases when I have intersection, 1 intersection or 2 intersection? So remember that we are taking this number of intersection as the value of function n, and this function is an integrand of double integral. When you take a double integral, when you take a integration over zero area region, such as curve, then integration is 0 because it doesn't have an area. So the double integration is basically area times the function. You need to have non-zero area to get a non-zero value of your double integral. Here, when does it have 1 intersection? Only at rho equals to 1. So it means that when you're taking the theta rho plane here, it's basically the rectangular region, but when rho is 1, you're looking at this one edge of your rectangular region. So if you want to integrate over this boundary, like one-dimensional edge of your rectangular region, the integration is always 0, no matter what the value of function is. So I don't need to have an exception when rho equals 1. I can just simply disregard the number of intersection when rho equals to 1 and consider that the number intersection is always equals to 2, because the integration over the boundary is always 0, doesn't affect the entire integration. So the number intersection is 2, and our domain of integration is entire rectangular domain, so 0, 1, 0, 2 pi. So you just take the integration, you get 2 pi, and when you take the 1 over 2 outside, right? So that's the boundary of your circle. So we're going to use this to actually compute any curve. So how do we use this? So let me explain with the situation here. So first, the circle is just an example. We're going to take the random, assume that we have a random curve on the plane. So as I said, we can approximate the length of a curve by the approximation, the sum of the lengths of the line segment joining the points on the curve. So these line segments are approximating lines of the curve. So let's take one of them here. So I take L here, or maybe, well, let's say L here. So I want to compute the length of this line segment. Let's say that's the ith length, the line segment that approximate the curve. So let's call it Li. So it's a line segment. So I can think of this line segment as if it's the same line segment we saw on the first example, which means that if I rotate this line segment Li to the position where its end lies on, one end lies on the origin and the other end lies on the minus axis of x-axis. So that's like this. So here we have line segment Li right here. By changing your axis, or you can actually move your line segment, doesn't matter. So this is your line segment. What was what was the result? We saw that it works. We saw that Cauchy-Grothin formula works. For any line segment lies on the negative side of x-axis, whose one end lies on the origin. So we can say that this is 1 over 2 of entire domain. Let's say the domain is the rectangular box that contains entire curve. So this is our D. What I'm saying is that so we have a rectangular region R, and D is the region inside of R theta plane whose image is the R. Okay, so maybe a better way to say this is I'm taking this line, entire line. Let's say this is the origin, 0, 0, inside a big ball centered at the origin. In that case, now how do you get the entire ball? Well, you don't want to think about the line segment that is lying outside of the ball. So what you want is you consider entire angle between 0 to 2 pi. And your distance from the origin of your line is as far as R, so 0 to R. So if your entire curve lies in this big ball, then your domain of integration can be simply the rectangular box like this one, and we're taking n of L theta theta rho d theta d rho. But here I'm taking just an intersection of my line L theta rho with the line segment Li. Okay, so that's why I distinguish it as Ni. Okay, so we saw that this is true. So this is what actually we proved in the first example. Now, what's the entire length? So entire length is approximately sum of each line segment. So we can take entire integration ni zeta rho d zeta d rho, and then so it has all the same integration domain. So we can put the symbol, the sum symbol, inside of the integration. So we can just take the integration of sum of all integrand. So this becomes 1 over integrating over d of sum over ni zeta phi d zeta d phi. And what is this? So this is the number of intersection of the line L zeta phi with ith line segment and it's the sum of all number of intersection, right? So what is it? When you take an approximation by increasing the number of subdivision, this simply is the number of intersection of L zeta phi with the curve C, the original curve C. So that is n, our definition n. So that is equals to 1 over 2 d n zeta phi d zeta d phi. So we basically just proved the Cauchy-Crossland theorem, but we're not going to use this theorem ideally because it's hard to parameterize any given random curve in terms of zeta and phi. So what we're going to do is use the Riemann sum of this double integral. So whenever you try to get the integral, you have to think about how to get approximate value. So think about this as approximation of sum with a large sum now, but don't think about it as a sum of the small line segment or something similar to that, but think about just the integration itself. How do you approximate this integral? First of all, you just subdivide your integrating domain into smaller parts. Here, the integrating domain in two-dimensional region, so you have to subdivide your two-dimensional region D into smaller region Dij. So this is going to be 1 over 2 ij. So I and j are indices for x direction and y direction. Let's say I take the partition each axis by n subdivision, and let's say n zeta I phi j delta phi delta rho j. That's your Riemann sum, right? Now, what does this mean? So this means that it's the number of, I'm going to write it again, intersection of L zeta I phi with the curve C. And what does this mean? So this is the length of subinterval, but when you integrate, when you use the Riemann sum in order to get approximate value of your integration, usually you take the equidistance partition. So these are always the constants. So these are replaced by simple constant delta theta and delta rho. So what is delta theta? It's it's the increment. So increment of theta in the partition of the interval from 0 to 2 pi. So you need to take the partition between 0 to 2 pi. If you take the n subintervals, you take 2 pi over n subintervals, length subinterval. So this delta theta is 2 pi over n. And the delta rho is the same. So you have a certain distance, a certain range of your rho. You take the equidistance, and that's your delta rho. Now, as I said, our intention, our objective is that when we have a curve on a certain region, a rectangular region, like random curve, I don't know, whatever, we want to find its length, okay? So we don't know the parameterization, so this is curve. We don't know the parameterization of the curve, or we're not specifically bound to one type of curve, which means that we want the algorithm finding the length of a curve to work for any curve. So if you just want to find the one curve, one length of one curve, then you could have, any particular ways to find the length, but we just want it makes to any curve, any type or any shape of curve. So that means we cannot just take the arbitrary number of subdivisions. We are going to fix our subdivisions. We're going to fix the number of partitions. We're going to fix the way we're going to partition it. So how are we gonna do it? So let's see. Since we are taking a strict or unchanged range of our rectangular box, the rectangular box is fixed. So we're going to have a fixed row or a fixed angle. Angle is just 0 to 2 pi, but let's say there are going to be always a fixed distance that we are going to try to measure, try to compute all the intersections. So this means that the range of row is fixed. But let's think about not in terms of range of row, let's think about in terms of delta row. So all we are going to do is just take all possible line and take the number of intersection with each line, right? So how are we going to take all possible configuration of line? So think about this way. How are we going to take all possible configuration of line? Well, in practice, in reality, you can't. You only can change your angle continuously in an ideal situation, but in a real practical situation, you cannot really change your angle continuously and try to measure all possible intersection. And we don't really need that, because all we are going to do is approximation. So we're gonna set the increment of your angle and increment of your distance so that you have a discrete configuration of lines. We take discrete configurations of lines. So how? We fix delta rho and to a certain amount, let's say, well, just delta rho, and also we fix our delta theta. So what I mean by fixed delta theta, let's say start from the theta. You have 360 degree in order to get all possible direction of your line. So let's take 4 partition. Okay, I want to make it into 4 different directions. That means you have either 0 angle or pi over 2 angle, or let's see, another minus pi angle and another 3 pi over 2 angle, and so on. Those 4 directions. And let's say we want to take a row from 0 to 10. Okay, then I also want to partition that range from 0 to 10 into 10 partition. That means you have either 0, or maybe you don't want to, yeah, but 0 and 1, 2, 3 up to 10, but actually that's 11 partition. But anyway, so you have those kind of discrete configuration. So combining all the combination between the row, this discrete list of row from 0 to 10, and also discrete list of theta from 0 to 3 pi over 2, you get all the discrete configuration of your line. So here, let's see, I have 0, 1 up to, let's say, r times, and 0, 2 pi over, let's say, n up to just before 2 pi, because you don't need to include 2 pi because the same as 0, and minus 1, 2 pi. So you have this way, this much, let's say this r minus 1. So this is r and this is n. So you have rn number of different configuration of your line. Now, for each configuration of a line, you have certain line, you have certain, place, you have certain configuration of your line. Then what you do is, let's say you have a curve on your screen, let's say like weird curve. So you have, this is your line segment that is in one of this configuration. So this is theta I and rho j. You compute how many intersections are there. So you're not really put the line on the screen, but you just imagine if it's a series of pixel points. As I said, I'm taking this line into a computer screen, and then you take the pixels, just examine the color of this pixel along the line, and then see if there is a change. So what I mean by that change is that, let's say the screen is all black except for the pixel that represents a line. So if there is an intersection, if you take the color pixel along this line and you translate it into a graph from here to here, then it's all 0, and then you translate the color information of white and black into 0 and 1. It's all 0 except for a certain point you have peak at 1, and then it's also 0 again. But if you don't have a 0 black color, and if you have a gray color, it might look like non-discrete, something like these kind of graph. But at least you have a certain peak. So you just need to count how many peaks are there along this line, and you do this for Rn different configuration of your line, and that's your number of intersection. Okay, so and then once you count all entire intersection, going back to the original summation here, these are constants, so you can take out from the outside of summation. What you are doing here is just taking the summation of all the intersections, right? And then you take the multiple of the increment of theta, increment of rho, and divide it by 2 to get approximate of your length of a curve. So we're gonna do it, we're gonna actually implement this in the Python code. But so here we need to decide before we start coding. So as I said, here still represented as a number. You can increase the number R and N in order to get a better approximation, but then you have more computation and you have more things to consider. So, and also when you think about the pixel aligning to somehow with the non-vertical or non-horizontal direction, then you have something to think about a little bit further, because the pixels are not really aligned in that non-horizontal nor non-vertical direction. So what I'm going to do is I'm assuming that the theta is actually differed by pi over 2. So I only consider horizontal line and vertical line. And my rho, well, it actually depends on how big is your screen or how big is your the image size. So I'm using 800 by 600 pixel the size screen for my program. So I take the rho to be 10. So which means that this is considered as length 1. So you can imagine that each pixel represents unit length 1, but I just took 10 pixel as one unit of length. Okay, so in that case, I took the delta rho to be 10. So what I'm doing here is I take an imaginary line, vertical and horizontal, which are separated apart by 10 pixels. So 10 pixels, like this one. So this distance are all 10 pixels. And also vertically. So there are basically 81 or 80. It depends on where you start from. But on the boundary of this screen, it's hard to imagine that there is a curve drawn on the boundary, so you can exclude the boundary. But so you can just take the 80 lines, vertical lines, and 60 horizontal lines here, separated apart by 10 pixels. And then for each line, I take how many intersections are there with the straight line and the given curve. So how do we get the given curve? So we're going to draw it. We're going to actually make it into a game. So the game basically means that the user can interact with the program, and then program has a feedback depending on the input. So user draw the curve in the game, and once the drawing is completed, then it will show how long is that curve. Okay, so all right. So before we begin, well, let me. I want to take some question if you have any, because I just explained without any break. So we're gonna implement this, and then you will understand it a little bit better if you see how it works. But besides that implementation, if you have any questions about the theory behind, let me know if I can explain again. Okay, so so this is the working code. So I think you should try putting this code onto your computer, but you shouldn't use the Colab, because this one requires a pop-up window. So you have to open up your local IDE, such as PyCharm or VS Code, and You can try with the Python notebook environment, but I think it works best if you use just .py file. So let me show you one example here. Oh, not this one. Okay, so it might be a little bit different from the code, but basically it works the same. So what I did is I defined a Python file. I made a Python file .py ending with the .py, and I simply copied all the code. You can do the same thing with the code on the slide, and you can run the code by pressing this button. I think it will pop up which Python compiler to use when you do that, if you have a Python installed on your computer. But then what happens is you have a cute little icon appeared here, and it pops up pop-ups the game window. So I think I showed you in the beginning when I explained the code, when I explained the project. So when you do this, it doesn't have to be closed curve. It draws the curve when I press down and hold the pressed, and then when I release the button, then it computes the length of a curve and it shows you the length. And you can actually add more curve. So you just add more curve means add more length. And if you click the right click button, it resets and the length goes to 0 and so on. So basically it's a game technically, but there's no element of competence, compete and more randomness. So you can add more of the fun part of the game to this type of prototype game. So yeah, I think this code is a little bit let's see, not efficient. So let me make one more. So let's do it one by one together. So if you're going to type in anyway, but why not type together? So curve 2. So I'm gonna use Py code here, .py. So I'm gonna show you from not from beginning of the code in the slide, but from the way how you actually code or make a program. So basically, we're using Pygame. So you can Google Pygame to see the documentation. It's a really nice documentation considering that most of Python packager has a very bad documentation, but the Pygame has a lot of very nice documentation. So you can read, if you need some other functionality of Pygame, you can read the documentation to find out what that is. So here, this is the basic structure how you make a Pygame, a game with a Pygame. So you take this way. So what happens is, when you run the game, you have a screen, right? And the screen is actually refreshing its color or pixels in the colors in the pixel in a certain number of frames over each second. So if you think about, if you saw some monitor spec that says 30 frames or 60 frames per second, and that means it refreshes 60 times your screen for each 1 second. So what happens is, in the same thing, similar thing happens. Basically, it's the same thing, but it goes infinite loop because it has to refresh your screen all the time. So your infinite loop must be in the form of while. It's the best way you can make an infinite loop. And the loop condition is always true unless you press the X button, which means it closes the window. So how does it accept whether the click of X button occurred? It is done by taking the Pygame event class and get function. So whenever you call this function, it always tries to detect whether there is an input or whether there is some user input to the window. So if that detects an event and an event type is Pygame quit, that means pressing the X button on the window, then it makes the play to false value. That means whenever next time the loop continues, the condition is false, the loop ends. So the loop goes outside. So in that case, you have to always use Pygame quit. Oh, sorry. So you have to use the Pygame init first. Pygame init and quit. So in between init and quit, you have this infinite loop. Okay. So without this infinite loop, Pygame doesn't work. And without this condition, this is most important thing. Without this part, when you press X button on the window, it freezes, and actually it crashes. So you have to manually close the window. That's not the way you should work. So you should have this basic code as your backbone of any Pygame. So when I run this, oh, I think I forgot. So nothing happens because I forgot to put the display. So let's put more display. Pygame, let's say display set mode 80 by 600. So let's see. Yeah, so now it has a window. So it's a Mac based, so the X button is in a different place. But when I press X button, now it ends. Okay. So without this part, when you press X button, it freezes. So basically, you can see what happened. Init has all the background work contained. It contains all the background work, loading on game engine and so on. And then display set mode actually displays the window, and then the whatever goes inside should be in this form. And then when you break the loop, that means Pygame is, the user pressed the X button to quit the game, so you have to quit the Pygame. That's all. All right, so let's do this one first. I want to, let's see, make a circle appear whenever I click a mouse button inside of the screen. So you have to. So as I said, this part always takes an event. So if it events in the Pygame quit, it fail. It makes the play false. But if the event is type of Pygame mouse button down. The mouse button down means it's pressed. So mouse button down, and you can see that it's auto-generated, but I'm not going to use this. You can check which button of your mouse is pressed. Basically, there are three types of, actually more, but there are basically three types. One is left mouse button, and second is right mouse button, and the third is the middle mouse button. The middle mouse button is actually from the old mouse shape. We probably haven't seen this before, but I have. But now it's integrated into the wheel. If you have a wheel, you can actually press the wheel sometimes. So that's the third mouse button. Anyway, so we want the left mouse button to be checked. So just take the mouse get pressed as 0. So this means that if left mouse button, which is the first mouse button, is pressed, then it's true. Then what happens is I want to take the coordinate where the mouse button is pressed. So Pygame mouse get position, and then I want to draw the circle, a filled circle. So draw class has a circle function. Now, when you draw something, you need where to draw. You need a destination of your drawing. So your destination is the entire screen. So where is that screen? The screen is the output when you first display your window. That when you run this code, not only makes appears the window, but also returns the screen environment, screen class that you'll be able to put any object in it. So the screen is this one, and then you want to make the screen. So I'm just copy some part of the code in the slide so you can see the slide if you're following this. So, and also the color is white. So RGB color. So if RGB is the max value, all the RGBs are max value. It's white. And where x comma y. And let's see. Next one is the radius. So I'm gonna put the radius 3. So I think it's the radius about the pixel. So radius 1 means only 1 pixel is drawn. So it has a circle. When you have 3, then I think the radius, or maybe the diameter, the pixel-wise size is 3. So anyway, let's do this one. And once you've done this, so you see the for loop is done when they took all the events that took place, and then it goes to this part, and inside of this loop you had a drawing. So you have to make this drawing happen to your screen. So Pygame display flip does that. So I don't know why it's called flip, but anyway, it makes the drawing appear. So when I run this as it is, then I can click to make the dot appears. So you can, if you magnify this, it looks like a diamond because it's a small radius or diameter circle, but it looks like a dot when you look it farther away. So you can make many dots here. So only makes a dot. Okay, so it doesn't matter if I drag this points or not. So okay, so what I want is I want to able to draw the curve. So I want to draw the curve by pressing the left mouse button, pressing the left mouse button and move the mouse cursor. So that means when I press the button, I have one position. When I drag my mouse, I have new position. I want to connect these lines. Or you can have drag, and then after dragging a mouse position, you want to draw a next point on the new position, and so on. Well, let's try that one and then see what happens. So this is the event, and let's see. If after you handle all the events, after you handle all the events, if the mouse button is still pressed, then what you want is you want to update your new positions. Okay, so that's when you first press the mouse button, and then inside of the loop that goes forever, you also always want to check whether your mouse button is still pressed. So then you want to get the new position, new x and new y. So the new position of x and y, and then you want to so not drawing a line. I want to draw the point, right? So new game, draw circle on the screen with the new x with the same radius. Okay. So and then since now you're at the new position, you have to update your current position to the new position, like this one. Okay. So let's see what happens when I do this. So when you get the new position, you draw the circle, the same type of point on the new position, and then update your variable x and y, which represent the current mouse cursor position. So when I run this code, when I take the mouse button click, and then when I take this, movement of my mouse, it kind of draws a curve, but it's a list of points. It doesn't look like connected curve, right? So why is that happens? Because, as I said, it detects your event or your input 30 or 60 frames a time. I think it's 30, I think. At every 30, 1/30 of second, it detects any input, or maybe less than that. Anyway, when you move your mouse cursor, it takes, time to move your mouse cursor to here, and actually, if your movement of your mouse is less than 1/30 of a second, then it doesn't detect whether your movement actually pass through one point to another continuously. So somehow the computer detects your movement of your mouse cursor is jumping from one point to another, because it doesn't detect continuously. So that's why you have a list of points, not the continuous line shape. So what you want to do is connect these lines by lines, so that it looks like a continuous curve. So instead of just drawing the circle, I want to draw a line connecting the old position to the new position. So instead of circle, let's see, I want to draw line. So the draw class also has a line function that draws a line on the screen with some color. So this is the white color from position XY to the new position here with a thickness. I think this thickness is same as the thickness of the circle that we have used here. So I think this is diameter, not the radius anyway. So when I change this to drawing the circle to line, and when I run this again, so just run this again, now I get a straight line. Not straight, sorry. So now I get continuous line. Okay, now I get something to do with it. So, well, it only does the drawing, not erasing. So I want to have an erasing function. So let's see. So inside of the event handling, so when the right mouse button is pressed, I think it's 1, maybe 2. Let's try 2, and if it doesn't work, then change it to 1. So if the right mouse button is pressed, I want to erase the screen into entire black. That means I just fill everything in black. So I'm going to make screen fill black. Let's run this one. Okay, so when I draw this, I can click left mouse button and then do it more. But when I press right button, it's gone. So actually it's not gone. I just colored every pixel in the screen with the black color. So that's actually not removing it, and actually overlapping it with the black color. Right? So basically I done this curve generating part. What's the next part? We need a calculating part, calculating the curve part. So once you have a curve, and when are we going to let the program to compute the curve? So it's when we release the mouse button. So that means we finished drawing the curve. Or you can continuously updating the length of a curve too, but it takes a little bit more, the lagging time. So let's see, if, so here, let me press this one here. Let's put it here. So so when I press the mouse button, it either starts drawing the curve, or when the right button is pressed, it removes the curve. But if the event type is releasing the mouse button, that means mouse button up. So mouse button, it's the opposite of down. When you press the mouse button up, not pressing, but your finger went up from the mouse button, then you want to calculate the length. So let's say I want to find the length by a certain function using the Crofton length. Okay, and so I can get the length. I didn't define the function Crofton length yet, but let's say I assume the length is now a value, float value. I want to display the value, right? So in order to display, you need a font. Okay, so it's a way you can turn data into a graphical string. Okay, so you need to define a font. The font goes up here. Where is it? Wait. I think I forgot to put it on the slide. Okay, so font is here. So this is the font part. So when you call the Pygame font environment and there's a system font, so you have to have this name of font in your system. So I think almost all computer has this font. So Comic Sans, basically it's a font for the cartoon. I like this one, and also you have to specify the font size of your font, and you're going to, so Pygame font, sys font, and Comic Sans MS. I think you can use other font, but I don't know the exact name. You have to follow the exact name of that font. So anyway, so let's take that font, and I'm going to textify that font by rendering the string. So the length, I know I want to put the length here, so let's just, why not putting into a float value? Okay, so I'm going to turn my float type data into a string type data by using this format. So it's F on front, and the blue color is the format, abbreviation for format. And here %F means that it's formatting the float type value into a string. And okay, so I think I should put 0.1 at least, or 0.0. If I don't want, well, maybe if I can just put D here, but let's put 3. So I want to have a certain degree of precision here. So I want 2 decimal points. So I get this one, and then forgot what this true is about, but at least I want to have a 0, the white color font. So that's the color of the font here, color of the string that appears on the screen, and that's your text. And now you have to put your text into the screen. So bleep gives text into appeared on the screen. So, and also when you put your text, you need to specify position of your text. So let's say, okay, so the anchor of your text box is anchored at the left lower part. So I think you should have some distance, height. You should put the height, some height on it. Okay. So let's see how, let's just check whether it actually works, and then we'll see, we'll implement more. So let's, instead of using this length, because we didn't implement this Crofton length, just let's put the font, this text here. So let's see how it works. Okay. So when I press this, press down and then drawing the curve and then release the mouse button up, 0, 0, oh, 0, 0, 0 is black, so that's why it doesn't appear. I need white, right? So sorry. 255, 255, 255. So let's run this again. Okay, so that you can see it appears. So when I draw this and then release the button, it appears, but it's already appeared and it's appearing in the same position, so it's not changing. But when I press the right, yeah, it actually appears, because when I press the right button, mouse button, and I release it, I let the string appears whenever I release it. So that's why it has always a hello word. When I pressed it, it disappears. But when I release my second right button, it appears because I released. That's the condition that my string appears. But anyway, so that's how it works. So let's put, let's delete this. Okay. So I need to implement this Crofton length with a screen, right? So let's see. Let's think about how we can implement this. So this function appears here. I need to define this function above, actually before before or after import, but doesn't matter. But let's say I need to define my function before it appears. So it only takes a screen value. So screen has information about these pixel colors. So I'm going to take the, let's see. This is an old code, so I don't want this. Okay, so I want to have the entire pixel information into an image. I want to take that as the entire image. So Pygame surf array. So there are arrays 3D or pixel 3D. So I'm going to use pixels 3D function. So it takes the screen information, which takes which has a color information of every pixel, and turn it into a NumPy array image format. So I get the image and height and width is the height and width of this screen. Although we know that it's 800 by 600, but in this function it doesn't know. So that's why I have this height and width confirmed here. And let's see. What I'm gonna do is trying to turn this image into a 0-1 array, because it's either white or black. So it's black, it's 0, white, it's 1. So I'm gonna make a NumPy array of the same size of the image, and then width first. For each pixel or each index of this NumPy array, I'm gonna set the value of this variable none. So I just named it without any thinking, just the none. It means that not, I don't know, whatever. So it's always 0 or 1. So if the pixel image has non-zero, so it has a R value, the red value equals to 255. So this is only because I know that all the pixel value are either 0, 0, 0 or either or 250, 255, 255. So I only need to check the first value, which is the red color value of each pixel coordinate. And then if it's 255, it means it's what? White, right? So it's white. I take it as, let's see, if it's white, let's see. Let's take white to be 1, okay? And when it's not, then it's black, so there I take it as 0. So 0 is the background, 1 is the line segment, okay? So let's, okay, so then I've done this, and what I do is taking the number of intersection. So as I said, I'm going to take the lines, either a horizontal line or vertical line. So when I take the horizontal line, I take the horizontal line first. So I take the height, 0 to the height with a step. So as I said, I'm going to separate the lines by 10 pixels. So my step is 10. Okay, so I'm skipping by 10 steps from 0 to height. So I don't include the height, so which means the bottom line here, but that's okay because the line segment, the curve is not going to appear at the bottom. Anyway, so when I take the horizontal lines, I take the ith row, right? And I take the ith row, and what I need to take is I take this array, so it's a one-dimensional array, and it consists of zeros and 1. Okay, so and then I count how many peaks are there. Okay, so let me show you the picture here. So I think I put it here. So right here, why can I zoom in? I can't zoom in. So anyway, you can see the picture on the left here. It has a peak, 4 peaks, because here I take the line segment going through the middle, and it's cropped here. So actually, the entire picture has this W-shaped curve. So when I cross the horizontal line across this curve, there are 4 intersections. So when I take the num array horizontally in this way, then all the values are 0 except for these intersections where we have a peak. But this peak is not only for one point, because this line segment is not simply 1 pixel, it consists of 3 pixels continuously. So you don't want to just take the number of white pixels, because it's not the number of intersection. You want to see when does the 0 turn into 1. That's the count that you want to count. So here so that's why I need another type intersection function to count the intersections. So let's say intersection or count, let's say count here is 0 before I count anything, but I want to add the count by taking the intersection of this array. So just simply count how many times the 0 value has been turned to the value 1, right? So that's for the horizontal one, and how about the vertical one? For the vertical one, you have to go through the width. So you count the intersection by taking the vertical arrays. So that's how you take the vertical array, all the rows with the ith column, that's the vertical, right? So then you just simply take the entire count, that's the total number of intersection, and delta theta, as I said. Now, what's the delta theta here? It's pi over 2, right? So numpy pi over 2, and then okay, so I take the step size at 10, and okay, so that's a different from the slide. So in the slide, I took the same step size as 10 pixel, but I took 100 pixel as a unit length. But I said I wanted to take 10 pixel as the unit length. But so in that case, delta rho is going to be 1, so that's delta rho. And you have to divide by 2 again. And I think you have to think about this a little bit here. Yeah, that's fine. Yeah, okay, so that's fine. So that's the Riemann sum, basically, right? That's the length, okay? So let's try to implement the intersection here. Intersection. It only takes the array of zeros and 1. So I just want to see how many times the zeros turn into 1. So just run through entire values of array. What do I have to? Oh, take minus. Yes, because I only want to see the two consecutive numbers. So let's see. That's not what I want. So if so what I want is, well, that's basically the same slide in the code in the slide. I'll just try the same thing here. So I'm going to say take the variable is black to be true first. So assuming that the first pixel is black, and I move my pixel values or the value in the array from the left to the right, and I look at the value. If array has the value equals to 1, that means it's white. And my previous value was black. The black simply checks that whether I'm in the currently black, I'm looking at the currently black color or not. So if I'm looking at black color and my pixel has the white color, then it turns the black into white. So I add one count. And then, since I'm looking at white, I'm changing this is black to false because I'm looking at white. So, and when I look at the black again, then I make change of is black into true because now I'm at the black. So once I run this for every array or element, then I get the count because every time I turn my observation from black to white, I add 1 to the count. So that's my count, entire count of intersection. So count doesn't increase when white becomes white in the consecutive values. Okay, so I think I implemented everything. Let's try, and then if it doesn't work, then I will fix it. Okay, so, I think I forgot to import NumPy. So let's put the NumPy here, and I think it should work. Okay, so where is it? So here, oh, why is it ij? It's ij. Why is it ji? So I is the width, j is the height. No. J is a height, right? J is a height. So j is the number of row. So index of the row. So it's a ji, right? Okay, let's run this again. So height, width. Height is the row. Height is the row. Width is the I. Width is the column, right? The error occurred at here. Sorry. So it's not numpy array, numpy empty. Sorry. So I want to make an empty numpy array with a certain size. So, okay. So now it works. Now it should work. So it now doesn't have an error message, but I think I made the font as a color black. That's why I don't have an output here. Let's check. So we have a renderer function. 0, 0, 0 is black, right? So I need to make it into white. So let's change it to white. So yeah, it does appear, but I think I forgot to erase the length box. So let's see. So every time I release my mouse button, it calculates the length, the entire length of the entire curve. But then, let's see. What happens is, well, the problem is, whenever I press the mouse button first, I have to erase since I need to update the length, I have to erase the length box, the text box here. So let's see. When I press the left mouse button to make a new curve drawing, then I'm going to fill the black box here. So it means that I take a black color 0, 0, 0 and fill a rectangular region starting from 0, 0 pixel to 100, 30 pixel. So 0, 0 pixel is actually up the left top corner of the pixel of the screen. So that's how you. So here, okay. So when I release it, now the text box appears. I think, okay, so maybe I should, maybe let's check. Okay, so I think I made a box a little bit over the top here. So I think I should make a bigger box here. Okay, and then now you can see that it's whenever I press the button to make a new drawing, the length disappears because I filled that part with the black color. When I release it, now it computes the length again. It appears up here. So here, yeah, it works because now it doesn't have to. You don't have to worry about this. But anyway, so when you want to put more thing on the screen, you have to think about this case. So when you take the image of entire picture as it is, you are including these parts. So this is not a text. The Pygame considers this as an image. Okay, so when you try to compute the length of a curve of this image, including this text box, then it computes the length of this text image. So if you have something on your image on your screen in your game that is not related to the curve, then you should consider to exclude the calculation of that region. Okay. So that's basically the prototype of the game, but that's not a fun game. So you can make it a fun game. So if you have some story on it or some competing element to it, so think about how you can make it into a fun game. Also, if you think about how you could incorporate some other mathematical concept into this. Well, so for example, you can, let's see, well, think about making an area, right? That's actually the next project we're going to introduce, and somehow incorporate the areas and the lengths together. And also you can make it into different colors. So let's see, you have some objective that you need to draw curves in different colors with the different lengths. And let's say if you have a certain constraint, that always makes a game more fun if you have some constraint. So if you can do anything, the game is not fun. So put some constraints on achieving some goal, and make some make the game into a little bit more something that has a challenging part to it. So that might be a better game. So anyway, I'm just giving you a prototype of a game. It's not really. It doesn't have. You don't have to follow this exact exact shape or display of the game. I'm just giving you this could be done, and how the Crofton formula could be used in the game. All right, so I think we should stop here. So next time we're going to talk about the line integral and the surface integral. And the line and surface integral is actually the most important part in our integration stuff. So I hope you come. All the students should come. So I think less and less students are coming this day. Maybe after Thursday, some people might appear again. So see you on Friday.